Bonsoir tout le monde. Je m'appelle scientifique à l'éducation et au rayonnement de l'Institut Trottier de recherche sur les exoplanètes, l'IREX. Et je suis vraiment ravie, en mon nom et au nom de tous mes collègues ici présents, il y en a plusieurs dans la salle, de vous accueillir à cette grande conférence de l'IREX. Donc, je vous souhaite la bienvenue, vous qui êtes avec nous en personne à l'Université de Montréal. Je prends un petit moment pour reconnaître que l'Université de Montréal est située dans un territoire non cédé par voie de traité. On salue avec beaucoup de respect l'apport immense que les différents peuples autochtones ont apporté et apportent toujours à la vie culturelle et à notre rapport à la nature, j'oserais dire. On le reconnaît et on en est très reconnaissant d'être ici ce soir. Je salue aussi les personnes qui sont avec nous sur les réseaux sociaux de l'IREX. Vous savez, c'est retransmis en direct sur la page Facebook de l'IREX et sur le compte YouTube de l'IREX. Donc, je vous remercie d'être avec nous ce soir et je remercie tout particulièrement nos collègues d'Astropolie, un club d'astronomie de la Polytechnique de Montréal, qui sont nos fidèles collaborateurs depuis plusieurs années déjà pour nous aider à rendre cette diffusion en direct-là possible. D'ailleurs, si vous étiez ici ce soir ou si vous êtes avec nous, cette conférence-là est enregistrée. Donc, quand vous allez voir à quel point c'était une conférence incroyable, sérieusement, les personnes qui sont ici dans la salle, vous allez avoir tout un show. Vous pourrez recommander aux gens d'aller écouter la conférence en différé. Sans plus tarder, je présente un peu notre institut de recherche. Donc, l'Institut Trottier de recherche sur les exoplanètes a été fondé en 2014 grâce à la vision notamment de notre directeur René Doyon et de plusieurs donateurs, donatrices. Je salue en particulier Monsieur Lorne Trottier et la Fondation familiale Trottier qui ont rendu possible une immense partie de nos activités. Donc, merci beaucoup, Monsieur Trottier. On est vraiment ravis de vous avoir ici ce soir. Nos chercheurs, nos chercheuses se sont démarqués à l'international. Là, ça fait déjà 10 ans qu'on est sur la scène internationale. Donc, on est dans le domaine des exoplanètes, qui sont ces planètes qui sont solaires, qui sont en orbite autour d'autres étoiles que le Soleil, et aussi sur plusieurs autres sujets connexes, y compris le sujet, le cœur de la conférence de ce soir. Je ne veux pas voler le punch, ce que c'est comme sujet que l'IREX ne se démarque pas uniquement par son programme de recherche, mais aussi par son vibrant programme de rayonnement, d'éducation et de communication scientifique. On a une panoplie d'activités, d'initiatives. On crée beaucoup de contenu pour tous les publics, les petits, les grands, tout le monde entre les deux. Et la grande un des programmes forts de ce programme, une des activités fortes, devrais-je dire, de ce programme. Ça fait depuis le début de l'IREX qu'on a cette conférence annuelle où on invite un chercheur ou une chercheuse de renommée internationale pour venir nous parler d'un des sujets qui nous tient à cœur. C'est toujours une très belle occasion aussi pour les membres de l'équipe de connecter avec cette personne-là, d'en apprendre plus sur sa recherche, de développer des nouveaux partenariats, des nouveaux projets de recherche. Donc, on adore cette période de l'année. Donc, pour présenter notre invité, qui est une invitée très spéciale, j'invite notre directeur René Doyon sur scène.
Bonsoir tout le monde. Écoutez, c'est un immense plaisir ici de vous accueillir. Merci d'être là. Jackie, c'est vraiment une étoile, même si elle ne travaille pas sur les étoiles. Jackie vient du American Museum of Natural History. Elle a fait ses études de PhD à l'Université de Stony Brook en 2010. Ensuite, elle est allée comme chercheuse postdoctorale pendant 3 ans au Chili. Ensuite, elle est revenue aux États-Unis, à Washington, avec la très prestigieuse bourse Hubble. Et depuis 2016, elle est maintenant chercheur senior à MNH. Alors, Jackie, c'est une sommité mondiale de l'étude des naines brunes. Alors, vous connaissez sans doute les étoiles, les exoplanètes. Mais entre les deux, il y a ces corps étranges, des corps qui sont à la limite entre l'hypopée physique des petites étoiles et des planètes géantes. Et donc, Jackie a fait des contributions majeures dans ce domaine. C'est une observatrice aguerrie qui a utilisé tous les télescopes et elle va en parler ce soir. Elle a obtenu, elle vient de recevoir du temps très, très, très précieux sur le télescope spatial pour nous parler de ces mondes froids. Et Jackie, c'est aussi une communicatrice scientifique absolument extraordinaire. Elle est activement engagée, non seulement à faire des présentations comme ce soir, mais elle engage le public à faire de la science. C'est une de celles qui a cofondé un programme de science citoyenne qui invite les gens comme vous, là, à faire de la science et qui a mené, en fait, à des résultats vraiment importants dans le domaine de la recherche sur les naines brunes. Et finalement, ben, vous allez le voir, Jackie, c'est une communicatrice absolument extraordinaire. Quand on écoute ces séminaires scientifiques, il y en avait un hier, et qu'on regarde l'audience, tout ce qu'on voit, c'est un sourire sur la bouche des gens, et plus souvent qu'autrement, des gens qui rient. Et ça, c'est plutôt rare. Donc, en général, nos séminaires sont plutôt, bon, c'est des talks très, très techniques, très, très pointus. Mais Jackie a ce don de nous communiquer sa passion. Et donc, c'est vraiment un honneur de l'avoir ce soir. Donc, sans plus tarder, accueille avec moi Jackie Faherty.
Hello. Can you guys hear me? Okay, I apologize because I do not have any skills in the French language. Did Renee say anything mean? Okay. He didn't bring up politics or anything in my country. I just want to make sure. Two things to get us started. Maria, can we turn the lights? Test. I want to make sure this mic is okay. We're still good? Okay, because if it could be a little bit dimmer, that would be good. So, and the reason, folks, is because what I am taking you onto, and I've promised I'll stay on this side of the stage because I'm a walker while I talk, is because we're going to be using a planetarium software. And it's just better if it's a little bit darker because I kind of want you guys to feel like you're outside on a nighttime sky. You're looking up, you're enthralled. You guys know that there's a nighttime sky, yeah? And you can see stars? I use this joke in New York a lot because we can't see it. And also, it's important to know that this talk isn't just me, actually. I have a very, very important co-presenter. His name is Jonathan Gagne. He's here. Let's give him a round of applause, please. You don't even know why you're doing it yet, but if anything messes up, it's Jonathan's fault because he is going to be live flying for you in a planetarium software that we call Open Space. Open Space is NASA funded. It's also funded by a private foundation in Sweden. We collaborate on this software package. It runs in many planetariums across the world, and it allows us to immersively take you on journeys inside of real astronomical data. So it's something that I'm very passionate about having people know about because you could download it and put it on your own computer because it's all open source. So even if you want to play with the code, if I have any coders in the audience, you could, and then you could come to me and tell me that you've done that, and I could incorporate it in the main branch, and we could use it in planetariums across the world. Okay? All right. So we're going to get started. This is a tour. Think of this like Jonathan is your pilot and I'm your tour guide. I am going to take you on the journey. I'm just going to explain what you're seeing as we go along the way. And I'm going to be taking you on a journey that highlights worlds beyond our own. But I'm going to talk about worlds in our own solar system. And I'm going to be featuring the James Webb Space Telescope, which is NASA's premier telescope right now. By a show of hands, how many people know what even just the name James Webb Space Telescope? And it's okay if you don't raise your hand. Oh, I'm seeing most people. It's okay if you didn't raise your hand, but I'm already seeing some recognition. Great. All right. So let's start. Jonathan is flying. We're over a world. Anybody know what world that is? This is the easiest one. It's going to sound a little pop quiz you here, but just say it. What is that? Thank you. It's Earth. That's right. And let's pull away a little. And what city are we over right now? Oh, Jonathan's going in. That's good. See, he's piloting on his own right now. Do you recognize that? Montreal. We are over Montreal. We just took you on Blue Skies flight. We just lifted you off from the planet. You all just took off, or Blue Origins. You just took off on a Blue Origins flight and we took you into space. If we were in the planetarium, that would have gone over a lot better because we would be sitting in a dark room. But Jonathan did just take you up and over. Okay, so that's the planet Earth. And one thing about this software is that what you're seeing, and Jonathan, just give us a little bit of a spin so we can see even more of the planet. Do you see how there are, what are those white things? Clouds. That's going to be important in this talk. Clouds are a pain in the rear for people that study worlds beyond our own. They end up messing up your ability to do observations, but they're also beautiful. And all that you're seeing on the planet is the weather pattern as it was by a NASA satellite called GOES. So this is all real-time rendering of what the planet would have looked like if you were above the Earth. And we actually have it set to a date right now that is not today. Jonathan, what date is it set to? May 2020. May, what actual date in May? Oh, I love it. May 30th. So Jonathan chose that because I did tell him that that was real data. There's a nighttime side of the planet too, and we have a nighttime sky map. We'll wait till it comes back around. But that's actually real-time data that you're seeing rendered on the planet. It's integrated every 4 hours. So you're seeing what the weather pattern would have looked like integrated over 4 hours. So sometimes the weather blurs, but like Jonathan said, it was a clear day over Montreal, so you could actually see the surface. Well done, Montreal. Jonathan, let's pull away a bit from Earth and let's look at more of the things that are in here. So pulling away, good job. That blue line that you're seeing coming off of Earth is the Earth's orbital line as it goes around the sun. And now we've reached an area where you can start to see those little dots. You see those little dots? And we'll hold here, Jonathan, and then give us just a little bit of a spin. Yeah, okay. So all together now, what are those dots? Stars, which you can see in the sky when you don't have light pollution. I wish more people actually were outside looking at stars. Sometimes I call the nighttime sky the original Netflix. Do you guys have Netflix in Canada? Yes, you do. Probably. Yes. I don't know. I'm not from here, but it's the entertainment zone for everybody, right? Netflix and chill. It wasn't Netflix and chill. It's nighttime sky and chill back 150, 200 years ago, and then beyond that. So Jonathan's kind of moving us around. Oh, here we come. Does anybody recognize anything? Hold us here a little bit, Jonathan. That's the solar system, but do you recognize any star patterns? This is actually a pop quiz. You didn't realize it, but you get $100 if you get it right. I heard Big Dipper. I heard something else. Oh, I don't know French. Okay, I believe you. Yes. Jonathan, turn the constellation lines on so that we can also help this out too. So if we were to turn, so also what you're seeing is that's the sun at the center, that big bright dot. And then as you leave away from the sun, it's Mercury, Venus, third rock from the sun. You guys are nailing this. You're just as good as any New York City audience I ever give these talks to. And then onwards towards Mars and then the outer planets. So Jonathan has turned on some of the constellation lines. So there you have that blue line is the Ursa Major. The famous way to see the nighttime sky is that arc in the Big Dipper. You can see the arc there. If you arc, everybody knows this one. You arc to, I don't understand. Am I giving a talk to astronomers? Listen to you guys. Yeah, Arcturus. Amazing. And then what do you spike to? Spike. What is this? Is this an amateur astronomers group? Love it. Okay. So yes, this is how you might recognize your nighttime sky. And so just keep giving us a little bit of a zip around, Jonathan, and we can turn the constellation lines off. Although you can recognize them as you go. There's a beauty coming in. The Scorpion, a beautiful one. What star is at the heart of the Scorpion? Antares. I'm going to keep going. Who knows let's see. What's the brightest star in the nighttime sky? Aquarius. Okay. You guys are very good. I'm going to think of a good one that I'm not trying to stump you. What's that thing, that blurry thing at the bottom? No. Jonathan, bring us up. Bring it up. There's two of them. Other way. Yeah. The Magellanic Clouds. Yeah. Okay. So you guys are still doing good. Okay. And Jonathan, bring us over a little bit further so we can see the Milky Way, because this is actually what I'm trying to get to. All right. So we'll hold here. Now the constellation lines are there. You're doing great. He's doing great. He's doing great, folks. He did not know I was going to ask him to do this, by the way. I threw him in here at the last second. So that line of stars that stretches across the sky there, we call it the Milky Way. That is the galaxy that we live in, and it's a river of stars, right? Yes? How many people, by raise of hands, have actually seen the Milky Way? I'm not surprised, because you guys all seem like amateur astronomers. Great. Now, Milky Way, river of stars. We're on the inside. We're mapping it from the inside out. Beautiful. But when we look at that river of stars, notice that there's all these patches where you can't see through, right? There's dark spots. You see those dark spots? The dark spots are there, and you're doing great, Jonathan. We'll just let this keep going. It's giving us a little tour. Those dark spots. Those dark spots are dust. And if astronomers are answering, stop. It's for the public, I thought. I gave the science talk yesterday. And it's fine. You can answer. So it is dust. Okay. So there's a lot of dust between your eyes, because it's not a missing amount of stars. The next time you go out and look up at the Milky Way and you are excited when you see the Milky Way. Just remember, when you see those dark areas, those are giant molecular clouds that are absorbing the light away from the stars that are behind it. And they're preventing you from seeing the stars. You and your eyes, even though your eyes are amazing, they're so amazing that all of us can see each other right now. And when we go outside, we can read a book by the light of the full moon, which is stupidly silly that we can see in that kind of difference and contrast with our eyes. The human eye is amazing. If I had to rank human body things, it's not a weird thing, I'm just holding myself back, I would put the eye as one of the top things that humans have that I think is phenomenal. Okay. However, that still, your eye is limited in the wavelength that it can see. So we're stuck by only seeing optical. This is a lead up, because the telescope, the James Webb Space Telescope, NASA's premier telescope, does not look at the sky in the optical. It's not looking the way your eye sees the sky. So I'm going to ask Jonathan, not quite yet, Jonathan, but I'm going to reveal to you one of the ways that the James Webb Space Telescope sees the sky, because it doesn't look in the optical. Oh, can you still? Yes. It's cutting in and out, but I think we're good. As long as you're happy, I'm happy. It looks at the sky in the infrared. And I'm just going to give you a little bit of jargon here. How many people know the instruments on the James Webb Space Telescope? Oh my God. I think I'm giving my science talk now. Okay. So if I say NIRCam and NIRSpec and NIRIS, we're good? Okay. This is the astronomy department. I get it. All right. So it looks at the sky in near infrared light and mid infrared light. Let's look at what the sky looks like if we were going to do an all sky view using near infrared light, or what the sky looks like in the near infrared, which your eye doesn't see. So Jonathan will turn on the 2 micron all sky survey. What was that? Did you call it fire? Did you say that's fire? Oh, I thought I was like, let's go. That's fire. My name says that all the time. So I get excited when people say that to me. Okay, so let's blink it off for a second, reminding us what the sky looks like. I'm an astronomer and I love doing this. So that's the Milky Way. Yeah. On, off, on, off. Okay. So what do we get to see when we turn on the near infrared? We get to see the dust. You get to see through the parts that look like no light is coming. All of a sudden we see the light. James Webb is amazing at looking at the dust. Dust, 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 dust. James Webb is awesome at it. Near infrared light, it's nailing it. Okay. Now this is one of the two different kinds of instruments aboard the James Webb Space Telescope. The other looks at the mid-infrared. So Jonathan, let's switch from 2MASS and let's switch to the WISE all-sky image. Prettier colors, maybe. Again, you're seeing that light really glow. And Jonathan, just turn us a little so that we can see the Magellanic Clouds. So you had them on, and just bring the bottom back up and then turn us a little bit in their other direction. Yeah. Okay, so now you're seeing the Magellanic Clouds. They glow beautifully. We're seeing the dust in there. It's just a different wavelength that the dust is shining at, but you're catching it. And so this is to just give you an idea of how that telescope sheds light at a wavelength that your eye cannot tell. Okay? It's really important to understand that astronomy isn't just about what the eye can see. We'd be very limited if we were stuck in what the human eye was doing, even though I told you I think the human eye is amazing, right? All right. Now, here we are. Let's go back to the regular optical sky that we all know. And let's fly to the James Webb Space Telescope, yeah? Because we can do that with this software. So I'm going to ask Jonathan to target it, and we're going to fly past Earth, past the moon, to 1 million miles away from Earth, to location of the James Webb Space Telescope. You did it. You didn't crash. It's pretty easy to crash into things in this software. So Jonathan's going to give us just a little bit of we call it a turntable. So you'll just turn us around it. And we'll get a little bit closer, Jonathan. So this is the largest mirror for a telescope we've ever launched into space. It was launched in a compact form, and then it unfurled like a lotus flower. How many people watched the launch? Nice. Were you guys scared? Renee, did you think it was going to crash? Did we think it wasn't going to unfurl? Did anybody place a bet on off-track betting? Because you know that was happening, right? Did anybody follow what the odds were? I'm not going to say I'm a bettor, but I was following what the odds were that there was going to be a problem with it. I'm admitting something maybe too much, but a lot of people were putting money on maybe it would have a problem or not have a problem. It didn't. Is anybody here from Europe? Oh, a couple people. All right. So as we probably know, because I guess I'm talking to astronomers, the European Space Agency launched the telescope from French Guiana, and it was a pitch perfect launch. So congratulations to all the Europeans in the audience. Well stinking done. Gorgeous launch. So perfect. Beautifully placed. Beautifully stuck into orbit. Everything did so well. The telescope is now 1 million miles away at Lagrange point number 2. That's the sunshade that's about the size of a tennis court. Jonathan will take us around and we'll see the mirror again, which is gold plated. That's a 6.5 meter mirror. Light comes in from distant things, reflects off it, bounces off that secondary, which is at the top of the cage, and sends it back to the instruments where you have your near infrared instruments and your mid infrared instruments. The mid-infrared instruments are the thing that I'm most interested in right now, but the near-infrared instruments are also super, super awesome. Okay, so that is our James Webb Space Telescope. It has been in operation since 2022. It was launched Christmas morning, I guess, 2021. Sounds like everybody was watching, so you guys know this well. And we have just entered. Well, we just got the results for the 4th cycle of data that we're going to get to turn the telescope to. So I always tell people in public talks, I'm going to tell you a little bit of the tea. I'm going to spill the tea on how astronomers are getting data with this telescope. So once a year, all of us, out of doubt, like Clash of the Titans, Hunger Games, all those to see who will get to point that telescope at their favorite thing. And we have the entirety of the universe to choose as to what we will point this thing at. Will it be galaxies? Will it be planetary nebula? That's mean. Will it be young stars? Will it be exoplanets? I know that IREX is here. You guys should have cheered on that one. Or will it be brown dwarfs? Good job. I train you well. And so we can point it at anything, right? If there's many astronomers in the audience, I will tell you, I take this responsibility very seriously. This is the largest telescope, the largest mirror we've ever launched into space. This thing has the capability of literally uncovering the secrets of the universe. But it's not like there's a manual to doing that. You have to come up and formulate an idea, a concept. It has to be strong, it has to be interesting, and it really does have to be something that's going to be catchy and a result. So when you think about what you're going to point that telescope to, it can't just be that patch of sky looks cool. Let's point it there. It has to be well thought out. So let me talk about exoplanets for a second. So Jonathan, let's pull away from JWST just a smidge. Oh, and by the way, before you do, can you turn on the field of view? Let's make sure those turn on. The other important thing about this telescope, that's how it points. And then there's something called like safety, and it'll show you the safe zone. So the other thing is when we all duke it out for the, what will the telescope point at, right? Okay, so let's move it so that we can see it in view. So that's showing you JWST is very limited in what it can point out at any given time. And that is because it is at L2. It is in the position it is because it has to stay very cold because it's at infrared instruments. We can't have any thermal radiation. The Earth is actually too warm, which is why we're not. Okay, so there's a safety zone and that's what's up there. But let's pull away a little bit, Jonathan, and we can turn those back off. And let's pull out to a position to show you, here's the problem with target selection. When we all duke it out for what we're going to point at, we have an array of objects to decide from, not just should we look at the galaxies or should we look at the planets. So sure, we have our panels and we say, send me to the galaxies panel and I'll fight against the galaxies people. But say you send yourself to the planets panel and you're like, I want to fight it out for I picked the best target. You have a lot to choose from. So Jonathan, turn on the exoplanets. So there's our nighttime sky-ish. We're kind of flying around. We can see some stars, and I do not recognize where we are. All right, and now just let us do a little lap so we can see how many of them until we actually get to the Kepler. Oh, there it is. Everybody recognize that? What's that? I just said it. I gave you a cheat. You guys know the answer. Say it. Say it. Okay, thank you. I was scared. I was like, do they? They know. Bring Kepler back in too. Okay, so there's over 5,500 planets to choose from, right? So which ones are we going to point the telescope at? Which ones? This telescope is in it's taking data for its third cycle. Fourth cycle, we just found out there's only 8,500 hours that were available, and everybody dukes it out. You're not looking at all of them. We are not looking at all of them. So which ones should we look at? Which ones? I mean, that is the question. Which ones? We have all of these to choose from. Make sure you choose the ones that are going to yield big science results or big results for all of humanity. Do you hear me? I take this seriously. When we write our proposals, we're not just doing it because it's like, oh, this will be fun. No, this is for humanity. It's a legacy. We are picking, there's only one telescope like this, and it's not going to last forever. You got to pick correctly. Otherwise, the telescope will die and we will have missed our opportunity to see something interesting. So astronomers, take it seriously in cycle 5. Okay? All right. Now, I'm going to show you the first one we all got to see. So, origin story. In the beginning, there were the GTOs, the guaranteed time observations. That means there were the teams that worked on the instruments, and they got to decide what the telescope was going to point at. That version. They got to decide on the initial lists, like Renee, who's sitting with you. She's one of the ones that got to decide on the original targets. The rest of us had to fight it out, but the GTOers got to put down whatever they wanted to look at, okay? So you guys know the inside baseball. If you didn't, guaranteed time observations. They're over. It's over. They got their time in cycle 1, 2, and 3. And now it's for the rest of us. We got cycle 1, cycle 2, and cycle 3 as well, but we had to share with the GTOers. All right. On July, can't remember the date, 2022, the entire astronomical community got to see the very first images from the telescope. How many people had a watch party? Okay, I'm trying to get to less and less people. I get it. No, like you did or you didn't get a watch party? No. No. You had to have at least 4 people. That is what I am calling a watch party. That's Jackie's designation of a watch party. 4 people, and that's a watch party. I mean, but it would be like everybody gets into the conference room because in the United States, our president at the time, Joe Biden, was the one to reveal the very first image. I don't know if you guys followed that in Canada, but we had a huge watch party. In the US, he revealed Jane Rigby from Space Telescope was there. It was amazing to watch astronomy meet politics like that, because the pride that we had in the telescope and science was so strong. Great. That was 2022. Then the following day, we all got to see the other images. So Biden released SMACS 0723, which was the deep sky image of the galaxy cluster. It was awesome. Then the next day, we got to see all the other ones. And the very first exoplanet spectrum using the James Webb Space Telescope was revealed. Pop quiz. I was trying to figure out how to get to stump you all. It's okay if you don't know. I know. Starts with a wasp. Nobody wants to say. You can't say, Renee. All right, Jonathan's going to take us there. It's wasp 96B. It's wasp 96B. You guys kind of got it. Good job. And its distance is just over 1,000 light years away. So we have to fly really far away from our solar system to get there. But let's get there. Jonathan's flying us there. You can see we took off from the solar system. We flew through the stars. We made our way over here. And off we go into this area that looks desolate because it's very dark. It's too bright in this room. And I don't have all the stars on, but don't worry. And we've arrived. So Jonathan, turn us face on. The star is color-coded by its temperature in this software. So it's yellowish, which means it's a solar type star. Probably a G type. I don't actually remember what it is. The area around the star is the habitable zone. So red is a little too hot, blue is a little too cold, green is just right. So if there were a planet in the habitable zone, we would be super excited. We would be looking for liquid water and blah, 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 blah. WASP 96b wasn't that. You can see that the orbit that's going around, we can get a little bit closer to the star, Jonathan. Actually, before you do, turn on the 1AU line and then get us back to face on. So that's the 1 astronomical unit line, which represents where the Earth is relative to our host star. So you can see that our sun would be, or our planet would be in the habitable zone of this star. But the planet that they actually looked at with James Webb is not that. So Jonathan, let's turn the 1AU, or you can just come in. Yeah, just come in closer. Now you can see that line that's going around the yellow star is the planet WASP 96b. So it's going around very fast. And Jonathan, if you have the star targeted, yeah, there you go. Jonathan's an amazing pilot. You already knew it. So it's going around at what rate did you set time to? 61 hours per second are going by. So you can see the rate of rotation, the rate of the orbit. It's 1 year in our world is 365 days. This thing goes around just every 5 or 6 days, zipping around. So in astronomy, we're very good at naming things. This is like a half Jupiter-sized planet, and it's really close to its star. So it's a half Jupiter mass-ish, really close to its star. So it's going to be very, 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 very warm. So we call it a hot Jupiter. It's a class of objects. That went over so much better the other day when I gave this to a public audience. You guys know too much. And you're like, yeah, we called it a hot Jupiter because that makes sense. It's a terrible name. It's not even a good way of calling it anything. Okay. Hot Jupiters. This is a hot Jupiter. It goes around every about 5 days. And what we did with the James Webb, it was like fish in a barrel. It was like, let's just get this spectrum, transmission spectrum. Let's just see what it looks like. And so, Jonathan, if you turn on the Trifid slide, it'll just show the James Webb press release on this particular planet. So it's showing you how we looked at it. We looked at it as it passed in front of the star. We did a transit light curve. The starlight was blocked by the planet. It had a beautiful, beautiful, gorgeous, gorgeous transit. I mean, just pristine, as perfect as you can get. And immediately after, you can click to the next slide. All of us stared admiringly at this spectrum. This is also, all the slides that I have are press release images. Okay, and so this was just phenomenal, right? How many people have seen this before? Most of the audience. Great. Though I see a little one back there. I don't think the 2 little ones have seen it. Did you guys? Do you little ones? I'm staring at you. Did you guys see it? Do you know what this is? You can answer. No? Do you like it? It's nice, right? This is the spectrum. Now I'm going to talk to you guys. Okay. Because everybody else knows what this is. So I'm going to talk to the kids. Okay. So notice the wavelength. If we all know so well, what instrument is this? Chloe? Okay. Yeah, it's nearest. Okay. You guys know what you're talking about. Okay, so 0.75 microns to 2.75 microns. I like to tell this to audiences, to the public audiences, because it's important. This is a spectrum that shows you the data with the error bars. This is how science gets done. All of the dots, it's kind of hard to see here because of the lighting, but the dots show you the best. We had to extract this out from the starlight. So remember, we have to subtract out the star's light to get to this. And then you would be able to see the dot, which is our best fit points, but an error bar associated with each point. Each point has a realistic error bar. Now, the ups and the downs, good job, Jonathan. I'm just zooming in. Go for it. And we notice that the bumps and the wiggles, the mountains and the troughs are telling you very clearly that you're seeing the signature of water. Water. Always sounds exciting, but this is water vapor in the atmosphere of a hot Jupiter. So we knew it was there. This was just a case study and a test. But the abundances of the water were less than we expected, which indicated that it also had clouds. So boom, we were up and running. Let's go. WASP 96b. And that cracked open the game of studying objects with James Webb. All right. We'll turn this slide off and let's go back to home, Jonathan. And now I'm going to tell, so because we have so many astronomers in the audience, we all know what happens next. The exoplanet community goes cray-cray and starts going after every kind of target they can think of. The hot Jupiters start winning out. We get amazing spectra of them in transit, in eclipse. We're seeing stuff. It's really exciting. I am a brown dwarf scientist. What are brown dwarfs, for those that don't know? Brown dwarfs are in between stars and planets. So Jonathan's taking, we can hold there, Jonathan. And so just do a little lap. Let's just give a little bit of motion. So all of the objects that are circled are stars that have an exoplanet around them. And so they reach across the cosmos. And actually, it's fine to do this. I wasn't going to do it, but actually fly us all the way back out so we can see the distribution. So keep flying us out. We're going to actually get a little bit of a galactic view. So there's going to be our exoplanet. Okay, keep going. It's fine. Keep going. Keep going. It's too dark in here. Well, just keep going. Okay, here's the galaxy. Keep going. Yeah, and let's do a little lap. So, and then turn the constellation lines on so we can see back to where we came from. So this is our Milky Way, right? I do this with exoplanet astronomers a lot, and they don't realize the distances that their exoplanets are from in the galaxy or the distribution that we're really looking at. Okay, so when we all think like, we're amazing, we've mapped the galaxy, we see the exoplanets, we're nailing it. That's it. That's what we got, which is amazing. But okay. I'm not trying to put down our field or anything, but like we're hanging out in a spiral arm. We're in the Orion spur on a spiral arm. We can't even see across the center of the galaxy. We don't even know what's happening on the other side because we can't see through it, which is fine. But maybe that's where all the aliens are, over there, hanging out over there. Right, you can just give us a zip around. It's just to say, like, yes, we're nailing it with exoplanets, amazing. But we are, you can kind of see them farther away from home, but they're really not. We're not really stretching that far out into the galaxy. So let's go back home, Jonathan, because I'm a brown dwarf scientist, and I was trying to set this up so you appreciate brown dwarfs. Now, brown dwarfs don't get us across the galaxy. But what they do is that there's a lot of them. There's a lot of them in your neighborhood. So get us a little bit closer to home. And you can actually leave the constellation lines on and hold us here. So I'll introduce you to this idea. So the peak of the distribution of stars, of kinds of stars in the galaxy, peaks in the M types, or they're low mass. Our sun's like a middle-sized star, and then it gets way, way less massive, fractions of our sun's mass. Okay, so this is our solar neighborhood. We're kind of hanging out probably right here at I would say that we're probably like 25 to 30 light years from home where we are here. Now, all of the lines are pointing back to home because these are the constellation lines that show you how we come up with these like figures in the sky, and then you get these constellation lines, okay? There are a lot of stars, and they peak at the late type M's. Your eye cannot see most of them. You just can't. The closest star to us is Proxima Centauri. You can't see it. We all know that, right? Sometimes I say this, and people are like, what? Like, you cannot see it. It is the closest, but it's too faint. They're intrinsically too faint, and it's a mid-M. It's not even like that crazy. So just imagine there's a world of objects out there that your eye can't see that are in your backyard. That's what the brown dwarfs are doing. They're literally in your backyard, but you can't see them. So it took us a really long time to realize they were there. So Jonathan, you can turn on the brown dwarfs. They contribute to your neighborhood. And I'll tell you part of why I love them and get excited. Why didn't you ooh or ah? Can you turn them off again? But hold there. Just turn them off. Okay. Do you guys like what you see? You like that? There's a lot of them. There's a lot of them. There's a lot of them. And they are literally your backyard neighbors. And okay, so don't you think you should know all your neighbors? Doesn't that feel like the right thing to do? Like, okay, it's us. And then the closest system is Proxima Centauri, which is with Alpha Centauri. So what's the second closest system? Clem answered, and she knows the answer, of course, because she's an astrometrist. Barnard star. Yeah, Clem, don't answer this one. What's the third for $100,000? Who can tell me the third closest system to the sun? I know you guys don't know it. It's a brown dwarf system. That's why I know you don't know it, because you should love it. It's called WISE 1049 AB. Sometimes we refer to it as Lumen 16 A, B, and B because a guy named Kevin Lumen discovered it. It's two brown dwarfs orbiting each other. And the year that it was discovered, of all our third closest, 2011 How many of you were born in 2011? The whole room better. Oh, you kids, you weren't around. Okay, so it's new for you guys. Okay, but just you. Fourth closest system to the sun. If you didn't know the third, you're not going to know the fourth. Another brown dwarf. Third and fourth, people. Fourth closest system, and that was discovered in 2012. It's, what year is it? 2025? That's not that long ago. That's like waking up one day and looking to your left and sitting in your bed is somebody new. You're like, where'd you come from? They've been there the whole time. That is the brown dwarf scenario. They're there, they're waiting. And I'll tell you what they do. They are in the wheelhouse of James Webb because they give off all their light where James Webb is looking in the near infrared and the mid infrared. That is why they are such amazing targets for this telescope. And they get colder and colder all the way down to the mass, to the temperatures that are almost reach Jupiter. But the benefit is that they do not have host stars. They're alone for the most part. A couple of them have a companion, but most of them don't. I'm going to end by telling you about one, my favorite. I've been using the James Webb Space Telescope to look at many of them. Well, as many as the TAC would allow me to look at. Because I told you I take it very seriously what I ask the time allocation committee to point this telescope at. So we found one, and if you turn the constellation lines on, Jonathan, it's actually one that my team discovered, and we discovered it in 2020, maybe. And then turn the labels on. It's in the constellation of Sagittarius. Oh, that's the constellation boundaries. Just the labels. If you do the drop down and then you click labels, because I can't. Okay, awesome. So let's just keep flying until we see Sagittarius. We're kind of in the north. Yeah, you'll just kind of move us around. We have to bring up the galactic plane and then we'll start to see it. Everybody remember these constellations? Cepheus. Oh, up. I like this. Yeah, it's towards the Milky Way. Don't worry. Don't harass Jonathan. I told you I asked him late in the day to do this for me. Here comes Gemini. You find it eventually because it's a circle. Don't worry. Just keep moving and we'll find it. Ursa Major, Canis Venatici, Comber, Booties, we'll keep going. Virgo. So it's a zodiac. So it's going to line up with the other zodiacs. Libra, you're doing good. It's coming. Scorpius, Sagittarius. Okay, here it comes. Good job. And we're going to pull in. So it's in the constellation of Sagittarius. So it's the one that we're kind of just peeking out. It's 35-ish, maybe 40 light years away from you. Or whatever. It's 11 parsecs. You're an us audience that knows what I'm saying when I say that. Okay. So what we did is we pointed at it. It was cold. It's about 450 degrees Kelvin. Jupiter is like 165 degrees Kelvin. So this is warmer than Jupiter. We wanted to see what it looked like. So Jonathan, you can bring up the next slide, which I don't actually remember what we called it, but it's the third one. All right. So this is what we saw with the James Webb Space Telescope. So because this audience is so amazing, what instrument did I use for this? If you look, so you have to, oh, that was good. I didn't realize it said that. Okay, nearest bit, but what grading did I use? New quiz. And you can't answer if you were at my talk yesterday, or you can because it means you were paying attention. What grading did I use? Oh, somebody says it. G395H. Somebody paid attention yesterday. Yes. G395H. What? That is an amazing grading. It gives you a high resolution of about 3,000. Every one of these wiggles that you're seeing is a real feature. It's a feature of a molecule that is doing something in the atmosphere. Now, we looked at WASP 96b. Awesome spectrum. Adorable. This, state of the art. Chef's kiss. Guys, seriously. I told you there were the dots and there was the up-down lines that showed you the uncertainties. I can't even show you the uncertainties. They're so small. That's how good this data is. Also, every wiggle is literally a vibrational mode of a molecule. Okay? So we got this data and we were blown away. And there's 13 other objects that were in this program. We looked at all of them. We were like, oh, that's right. There's methane in here. There's carbon monoxide, carbon dioxide. I pointed all of them for you. But I want you to focus, sorry for those on StreamYard, but I want you to focus on this area here and see if you can find the thing that we found right away. There's something weird. There's two objects, I should say. There's two objects overplotted here. They're on top of each other. They're on top of each other. One's on top of the other. And for the most part, they're identical, except for one weird thing in the blue object. Look at the blue object versus the white object. Little ones. I want you guys to see this. It's like doing science together with the whole room. Do you see between the number 3 and the number 3.5? You could zoom in on it, Jonathan. You're doing good. If you see, it comes up a little bit. The other one just stays flat. If you go to the next slide, Jonathan, it'll be zoomed in on it. It's important because what we do in astronomy is look for this kind of thing. Okay, so now we've zoomed in on it, and you can see the blue went way up where the white one stayed flat. So the flat meant that there was no flux coming out. All of that was being absorbed by the molecule methane, carbon and 4 hydrogens, which is pretty typical. We see that in a lot of objects. Makes sense. It's a molecule and it's absorbing. But instead, in the other objects, we saw it go up. Why did we see it go up? It only goes up if it's getting excited. It's happy. You don't get happy on your own in space. Something has to make you happy. It's my public outreach way of describing emission. That's methane in emission. Energy hit the atmosphere. Well, that was our theory, and excited it. But what could it be? What could it be? So in order to solve it, why did we see the methane get excited? We turned to the solar system. So Jonathan, you can turn this slide off and fly us to Jupiter to give you an idea of what we compare all of our world in the brown dwarf science to. We compare it to one very important world in our own solar system, the biggest of all the planets, the one that I call the bouncer of the solar system. You could fit the mass of the entirety of the solar system besides the sun inside of it. The mass of Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, the whole asteroid belt, the whole Kuiper belt, the whole Oort cloud. It all fits inside of Jupiter. It's massive, right? Now, Jupiter is a phenomenal planet to study. It's got clouds. It's got a mass that we compare everything to on my side of the spectrum of things that we study in astronomy. Then it has this other thing that's going on with it. Jonathan will move us around till we see the Great Red Spot, which is a giant storm that's going on over it. But it's got something going on it that is pretty typical of something that happens on Earth too. So on Earth, we have solar storms that happen. And then when the solar storm goes off, it can send highly energetic particles throughout the solar arena, the solar system, and some of them reach Earth, slam into our magnetic field, and we don't die from radiation because we're saved by our atmosphere and our magnetic field. But instead, we get a light show. I'm sure you guys actually get this here in Montreal a lot, yeah? So I live in New York and I've never seen it, even though it kind of hit us the other day. What do we call this? Aurora. Northern lights. We get the northern lights. It's so awesome. So the solar wind, it hits the earth. It lights up like a Christmas tree. You get the green, you get the purple. If you go to the Montreal Planetarium, they have a beautiful show on aurora that they play. So Earth is not the only planet in the solar system that has an aurora. Jupiter has an aurora too. Saturn has an aurora, Uranus has an aurora, Neptune has, they all have aurora because the solar wind slams into the atmosphere and the magnetic field captures, and then you get the aurora. Okay. So, and that's great. So we started to suspect that methane emission we were seeing was auroral in nature. And when we turned to Jupiter for help with it, it was a great, helpful explanation, except our object had no host star to help. We have no sun to give off the plasma. So Jonathan, now target Io. But then we discovered something that was going on with Jupiter that we didn't realize, and that's that Jupiter has a second big contributor to its aurora. And that is a moon in orbit around it called Io, which Jonathan's going to fly us to. I sometimes see, this is imagery of Io from the Voyager mission. So pretty. Io is close enough to Jupiter that it suffers from some of the tidal forces from Jupiter. It's highly volcanic. It's spewing out lava. It's the most volcanic object in the solar system, and its plasma ends up slamming into Jupiter, adding to the aurora, creating methane emission. Amazing. We turned to that as the explanation for what might have been going on with our object, and we speculate. I always say this, I'm not saying we found a moon, but I'm kind of saying we found a moon around an object that has no host star. So some people would call that a planet, but I don't really care for the word planet right now because it's not very descriptive. So I'm just calling it what it is. I think it's like a moon because Io's a moon around Jupiter, and that's what we think we found that's contributing to this brown dwarf. Now, brown dwarfs, we've gotten so much spectra. It's been so great. We've been looking at all of the chemistry in them, and I want to end this by just hoping that I inspire you guys all to, when you look up at the sky and you see the stars that you can see from Montreal, you remember the things that you can't see, right? So your eye is only tuned in to the one little smidge of wavelength that we get from the optical. If you were to see, if humans had been actually tuned to infrared light, we'd all be brown dwarf scientists. I'm not kidding. I actually think that would be very, very true. So remember that the next time you go outside, that you look up, or the next time you judge a telescope proposal, because I can tell some of you might be on the cycle 5 tack. And so with that, I'm going to stop and take any questions that you guys might have. Thank you. I can also show you other things in the software if you're like, oh, now I'm curious. Can I see the hierarchical structure of the universe?
Hi there. All right, so I have this question. We didn't know there were brown dwarfs until very recently, right? So, do you think, in your experience, do you think there might be other things we don't see apart from brown dwarfs around us in the galaxy?
So that's a interesting question. I'll take it to the brown dwarf side a little bit more, because we started finding brown dwarfs in 1995. And the reason we started finding them is because technology caught up. So they were theorized in the 50s, and it was pretty clear to everybody that they should be there. But we had no ability to find them because observational studies didn't have infrared technology. So that question has more to do with, is there something theorized to exist right now? Because brown dwarfs were theorized, and then we searched for 40 years for them. There's nothing that I can think of that I could give you as an example that's theorized right now. I mean, you could say dark matter that we think is out there in abundance, and people see its influence. But I would also turn to, do I think we've found, is Proxima Centauri the closest star to you? How many people think, without a shadow of a doubt, Proxima Centauri is the closest star? Just one. Did you sense that I was going to also say no? So in 2017, I co-founded a citizen science project called Backyard Worlds: Planet 9. And we did it because after those third and fourth systems were found that we just hadn't been able to find, and they were in our backyard, I was convinced, and to this day I'm convinced, there could be another very cold world under the detection limit of our telescopes that might be closer than Proxima Centauri. So we started our project to hunt for objects that were very, very below the threshold of what technology can lead for us to do. And we found that object with the aurora, we found because of that drive that we had to try and find closer things. We have not found something closer than Proxima Centauri, but I'm not giving up that search. I'll probably keep looking until past retirement, which will be in a long time.
Hello. Hi. You mentioned the detection range, and I was about to ask about it. Well, how we have these cold worlds called hot Jupiters, and how cold does it actually have to be so we can't really detect it with James Webb?
Yeah, so I said cold worlds, and then I introduced you to WASP 96b, which is considered a hot world, even though it always means like, what are we referring to? So for planets, WASP 96b is pretty hot. When I start using the word cold, the class of objects I'm really referring to, and the exoplanet community too, that directly images really is kind of below 500 degrees Kelvin. 500 degrees Kelvin is starting to encroach upon like Jupiter's 165. So once you find objects that are that cold, they have to be very low mass. So that's why I want those worlds. They're going to be gas giants. We're not going down all the way into rocky world temperatures. We're not getting down into I'm not talking about that when I say cold worlds. I'm talking about gas worlds, the gaseous worlds. But gaseous worlds, it would be amazing if we had a library of objects that were Jupiter-like across the solar neighborhood, that we had spectra for, that we had their chemistry, and that we could compare and contrast, because then you would be doing comparative planetology. Their looks, the atmospheres that you would see would be very telling of their origin story, of the molecules that were around when they formed, maybe the metallicity environment that they were in, all of that. So the cold worlds really mean to me, and in this talk, just take it with a grain of salt, mean 500 degrees Kelvin and cooler. Hot Jupiters and WASP 96b, I don't consider a cold world. That's that thing is like 1500 degrees Kelvin. That's a warmer one. Any other questions?
Yeah.
Yeah.
How do you define a brown dwarf?
Oh, that's so loaded. You don't even know. Get me on a rant.
Okay.
Okay, so I'm gonna say about them that I hate. I'm gonna say it, Clem. So, all right, in mass space, well, okay, let's start at the beginning. Brown dwarfs, the way that stars form, you get a giant molecular cloud and it collapses and it fragments into pieces. And some of the pieces are big and some of the pieces are small. And in the theory of brown dwarf, it became clear that sometimes when you form objects, you can break off a piece that's so low in mass that the core can't get hot enough for nuclear burning, for the hydrogen and the helium to come together and start fusing. Okay. And that became the definition of brown dwarfs. And the reason why it happens is because in order to get hotter and hotter as you get lower and lower mass, you have to squish the material closer and closer together. But now you're talking about electrons. And I often describe electrons as like people on a subway car. If you've ever gotten onto a subway car and like it's empty, right? And you go and pick a seat. And then somebody else comes on next and they decide to sit right next to you. You'd be like, go away. Who told you? Why wouldn't you go over there? Like the entire space is here. So that's what I often refer to as electron degeneracy pressure, because the electrons don't want to be near each other. So as you start to push them closer and closer together, they push back. That's the equivalent of you like pushing that person to go, oh, sit over there. And so they push back and they won't let the core get hot enough. And so brown dwarfs are that hold zone where electron degeneracy pressure holds them at a certain radius and the core can never get hot enough in order for nuclear burning to occur. That's the high mass end, and it happens at about 75 times the mass of Jupiter. Now, the controversial part of all of this comes at the low mass end. So some people like to call that kind of evolution a failed star. Boo. Who said that stars were what we were all supposed to try to be? That's ridiculous. Brown dwarfs are amazing for who they are and what they are. They don't have to be stars. They're no failures. There's no failure in science. There's failing here. But because they don't have an engine, sometimes they refer to that. Now, that's the high mass end, 75 times the mass of Jupiter. Then you ask, okay, so can you have an Earth-sized brown dwarf? We don't know. No, you can't. I mean, maybe. Question of can you fragment off a piece from the molecular cloud? Because formation, I think, is the better way to define what they are. Sometimes people use 13 times the mass of Jupiter as the boundary because all beyond 75 times mass, you get deuterium burning, which is heavy hydrogen. So you can get deuterium, which requires just a lower temperature, so the electron degeneracy pressure doesn't get in your way. You can get that to happen all the way down to 13 Jupiter masses. So brown dwarfs are really in between the mass space between stars like the sun and planets like Jupiter, but they have a very, very, very difficult way to define. It's a spectrum of objects. They probably form like stars, but you could also probably form an object that's brown dwarf identical through the planet forming process. So it's not really because you could accrete enough material maybe and stick these objects around a star, or gravitational fragmentation and blah, 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 other things that end up forming things around stars. So formation is probably the better way to define what a brown dwarf is. But they're in the in-betweens between stars and planets. But they are not a failure.
Thank you. Thank you.
Question over here. Oh, online question too.
Yeah, and it's really related.
Oh,
So
okay,
maybe
go
I'll
with it.
just ask. So Sylvain Simard online is asking, and I think it's pretty complimentary, is Jupiter considered a sub-brown dwarf?
Ooh, yeah. Do you know that I think sometimes I hear the press, when they report science stories, they call Jupiter a failed star. And even though I just told you that is the incorrect way to refer to brown dwarfs, I take offense when I hear them refer to Jupiter as a failed star, because that's incorrectly using the term twice over. It's not a failed anything either. Jupiter is Jupiter. That's it. Jupiter is just Jupiter. But Jupiter definitely formed around, or I shouldn't say anything definitely, but we think we really understand the formation mechanism for Jupiter. Jupiter formed by accreting material around our sun. And that is a very specific pathway to formation. So it's locked into the category of what we generally refer to as the planets. So it is comparative to brown dwarfs in its properties, in its atmosphere, in its mass, but its core is probably quite different than the brown dwarf core. But we have no idea how to access the core of these objects because that's like a little bit beyond our technological capabilities. But so that would be a differentiating component between Jupiter and the brown dwarfs, if you could actually access the core of the object.
Yes, hello. So I was wondering what new information you need to confirm that there is a moon around the brown dwarf, and if we can know that there is a moon, can we learn more about what it is made of? Like, is it like Io or something else?
Yeah, I wish I would love to know if the moon hypothesis is the correct one. And we did just win James Webb time in the 4th cycle to go back after that object to try and characterize that system. And when we do, I don't think we are going to be able to. We had all these theories about proposals that we could write to try and see if it is a moon, if we could catch it transiting, if we'd be able to actually see it changing the light of the brown dwarf as it goes around. But that's a that would have been what we referred to as a Hail Mary proposal to the TAC. I don't think they would have gone for that. But instead, what I think that we could say about it is the influence it might have on other things that we see on the brown dwarf. So we did win recently time on the Very Large Array to go after the magnetic field of the brown dwarf that would allow us to put some constraints onto the plasma that might need to hit the magnetic field if we can measure the strength of the object. We also are going to remeasure the strength of that methane feature and be able to also use that in modeling, now that we have some information on the magnetic field strength, to also be able to tell what the mass of the plasma is. That would help us understand maybe what, if it's the moon hypothesis, how that might compare to what the influx of plasma that Jupiter gets based on Io. I think that's the best we're going to be able to do in the next year and a half. But ask me again in a year and a half after we see that cycle 4 data, and I may have better answers for you on that.
Perfect. I'm looking forward to that.
Any other questions? Are we good? Or do you guys want to see anything in the software? Okay. I wasn't sure on our timing, on how we had on timing too. We're good? Okay.
I hope this doesn't sound stupid.
Nothing sounds stupid to me. So
You mentioned that stars are
a little closer. Is it on?
I don't know. Yeah, I think it is. Okay. I was wondering if there's specific compositions, because you said that it was the dust that kind of like compresses, but do you need specific kind of elements for it to compress to make the dwarf? Or are there like, because you're saying the sun, it's like it creates a deuterium, and I was wondering if that's, I don't know if that question's making any sense.
No, well, so are you asking about the composition of the atmosphere?
Yeah, do you need specific elements to be able to compose a dwarf star?
Yeah. So do we need specific elements in the origin of these objects to create them so that they can just be brown dwarfs? That's a great question. And no, it's the same kind of stuff that makes stars. So it's all in the same, like, objects are kind of cooked up like in a kitchen, but the kitchen is the cosmos. And it's all the same basic stuff. It's hydrogen, helium, and then you get like carbon and nitrogen and oxygen. What really sets them apart is that they just don't get hot enough in order to look. Stars also have the same amounts of material, and what we try and do is measure the abundances of materials. So we look at the amount of carbon and we compare it to the amount of oxygen, and we say, does that look like the same ratio that we see in the sun? Or does it look like the same ratio that we see in Jupiter or Uranus or Neptune? Like, does that compare? And brown dwarfs, for the most part, have the same kind of ratio of elements that you find in stars like the sun. So there doesn't seem to be anything necessarily, there's nothing special required to form them. But the reason we see that spectrum looks so different is because the temperature of brown dwarfs is low enough that the chemistry that can get cooked up is going to produce molecules. It's like being in a laboratory, and we set the temperature and we set the pressure, and that's why you can get ammonia in the outer atmosphere. And Jonathan has us over Jupiter here, and you see the different colors. So Jupiter has kind of the redder areas and maybe some whiter areas. And if you go in a little closer, although that'll cause it to go a little crazy, you might see some bluer areas. And that's all because of the chemistry that gets cooked up on Jupiter. So you can start to see like there's some blue, beautiful, beautiful cloud features. Those are all cooked up by the temperature and pressure on Jupiter. It's made from the same stuff our sun is, but the laboratory of that temperature and pressure is allowing for these phosphine clouds. So we think maybe the blue is maybe related to some phosphine clouds. on Jupiter. All of this is cooked up chemistry because of the temperature and pressure of that particular object. But the natal ingredients, the original recipe ingredients that were there, were the same as what cooked up our sun, because it came from the same stuff, and brown dwarfs are the same materials. We have one more back there if we have time, or over here.
You can hear me?
I got you. Yeah.
Great. So this might be a bit more of a ridiculous question.
No such thing. If you want to ask about aliens, here's your chance.
But you mentioned the main reason that the brown dwarfs don't turn into stars is due to the heat of the core not being hot enough to cause fusion.
That's why brown dwarfs can't glow the way they don't radiate the way stars do.
Yeah. So if you could theoretically, like, I don't know, drop a nuke
Add
into it.
Add mass. Are you going to ask the add mass
Just
question?
going into drop a nuke to make it hot enough.
Okay. I see where we're at. Huh? Only for hurricanes. Yeah. No one's ever asked me that part of the question. I think that would blow it apart. You need more mass. It's not about giving it, I shouldn't, let me try and answer this like I would in orders of magnitude graduate class. Like, you need to get the core hot enough. The electrons do not want to be next to each other, though. So in order to get it hotter, you need to move stuff around faster, and that will force them closer to each other. So the one thing, your best bet to do it, is to add mass to the system, not to try and blow it, to increase the temperature by inputting energy. That's just going to really blow it apart, I think. But I have worked on the question of whether, I've worked on the question actually with colleagues in both directions. Can you take a star, a low mass star, and strip material away from it so that you can turn the nuclear engine off and turn it into a brown dwarf? So a stripping concept. And I've worked with colleagues on the question of whether we could just start piling on mass onto a planet and turn it into a brown dwarf. Why would we do this? I don't know. Nature does a lot of things. Maybe you could have some binary systems where you have mass transfer. There's interesting concepts out there, but we don't have any evidence in any of the objects that we've studied that they're in that kind of category of objects, either stripped or added to. But it's a great, like, Einstein type mind thinking. He was very good at like coming up with these puzzle like questions to drive you down that was a compliment for you, by the way. I don't know if you caught that I called that an Einstein idea, but you're welcome. But that's a thinking kind of question.
What's the relative proportion of these brown dwarfs in the universe of stars? Like, what are the statistics? Are there be a lot more of them? Are they by far the most numerous things, or whatever? Does anyone have an idea of the statistics?
Yeah, our team has been working on answering that, because if you had asked that question 25 years ago, people would have been like, brown dwarfs outnumber the stars by some crazy number. And they were, for a very, very, very short amount of time, the candidate for dark matter. Does everybody know that? I've given a public talk on this where I think people didn't know, and they were like, what are you talking about? Brown dwarfs were thought to be, you can't see them, so they're an easy thing to be like, oh yeah, dark matter is just clumps and clumps and clumps of brown dwarfs. But then we started to search, and we found the numbers for them a little bit better. So the peak of the mass function in the galaxy is at an M5, so a mid-type M, and then it trails down. And so then you see less and less. But here's what we've found out. So basically the number that we see is for every star, there's one brown dwarf for every 6 stars. That's kind of the number. But that's for a specific range in masses of stars. What we have started to see, what we see hints at, when we include these coldest brown dwarfs, is an uptick, that we may be seeing more of them. Now, why? Why would that be? Why would it start to get more efficient at creating them? So is it possible that brown dwarfs can form in two different kinds of ways? Maybe, I don't know. You form the way that stars do, and so you're seeing the trail off in the mass function on the way stars form. But brown dwarfs overlap with planets. I don't even like to use that word, planets. Worlds is better, but they overlap in mass, and so it's possible that you eject a certain population of them. We don't know if that's the case, but we definitely see that when you get down to like 5 Jupiter masses in the isolated objects that you refer to as brown dwarfs, you might see an uptick. Jonathan has worked on this problem. When we look at the young moving group, we look at young associations and we try and see them as compact, isolated demonstrations of the distribution that you might get in mass, and you could see an uptick in the lowest mass kinds of brown dwarfs that we have. So the answer is maybe 1 brown dwarf for every 6 star, but not as you get to lower and lower mass. It looks like there's more of those that are out there. They're in your backyard. There's so many of them outside of your house.
Can the software go on TRAPPIST-1, my favorite failed brown dwarf?
Yeah. We could go to TRAPPIST.
Do you
love
have like
TRAPPIST.
how much exoplanets do you have on the software? I was curious.
Oh, this software is free. Oh, NASA gave us $10 million to develop this over 10 years.
But
$1 million a year.
Like, do you have a lot of exoplanets, like illustrations of a lot of exoplanets, or not all of them?
Oh, so that's the TRAPPIST star. So I often bring people into the Hayden Planetarium, which is also my affiliation, and at one point I had a computer scientist that really wanted to work on the software with me, and I had her putting in skins on the planets from artist renditions of it's kind of like eyes on exoplanets, if you've ever looked at that. We don't really do that in this software package. We try and use all of the data. So this is the TRAPPIST system. That's the red object is TRAPPIST. The green is the habitable zone, and you can see your favorite ones, whatever. I'll tell you, I gave a public talk in New York City right before I came here, and the last question of the night was from this guy. I was telling some of the astronomers in here, but I'll tell you guys. The last question in the audience on this talk, which was also on the James Webb Space Telescope, he was very, very upset. And he was like, I have to ask you. So I didn't show TRAPPIST. I didn't talk about TRAPPIST to him, to the audience there. I was like, I'm not going to talk about TRAPPIST because it's we're still waiting. And he's like, you didn't talk about TRAPPIST. You didn't talk about it. I want to know what's wrong with the spectrum. Why haven't the astronomers? What's wrong with it? TRAPPIST 1E, we know you have it. Where is it? Why haven't we seen it? So it's your favorite planet. And for all, because I know here at University of Montreal, you guys are working on this data. The public in New York City is asking. And I saw at the Extreme Solar Systems Conference some of the data. I understand. I defended all the TRAPPIST people in that public talk. I did. I stood up for it. I said, listen, Larry, or whatever your name, I didn't know his name. It's difficult to access data. And so, yes, we are trying to look at this thing with the James Webb Space Telescope. But that star is really active, and it's flaring, and it's hard to model. And we're trying to get to the light of something that's at the bottom of the barrel on photons. So I can't show you what it looks like, but other members in this audience here are going to be able to do that for you in a different talk. And that would be an encouragement for you and the general public that are here to come back to another public talk that happens here within the IREX team and with this amazing group of Montreal Planet Exoplaneteers, because they're working on, well, you're one of them. Yeah, you will learn the results of what is happening with this planet that apparently the general public in New York City is asking for, because there are planets in the habitable zone in this rocky world that's like 40 light years away from you. Yeah, so come back to another U of Montreal public talk. And thank you guys so much for And thank Jonathan for flying on the fly.
Thank you very much, Jackie. That was absolutely amazing. I told you she was great. She's great. She's funny. She's smart. We like to have a very good speaker like that. Just before we have a raffle, you all have your tickets. So we'll do that in a second. I just have a few thank you to say. So I just want to thank, of course, Jackie, because that was amazing. That was a great talk. Thanks a lot also for all the time you're spending with us. It's great for all of us. So we learn a lot with you. Thank you very much to René and all of the members of IREX, which were very numerous. And that shows how good the talk we had yesterday was because they wanted more. And also thank you very much to Astropoly again for that great streaming that was super, that went very well. A very great big thank again to all of our donors. And in the end, thank you very much to all of you who showed up. We really like to organize those events for you. So thank you very much. And if you want to see that presentation again, you know, you can go on Facebook or YouTube to watch it. Now it's the time for the raffle. We have very nice prize tonight. 4 prize. And one of them is a bit controversial, I'm realizing, Jackie, because it's a poster that we had made for the exoplanètes à l'école, exoplanets in the classroom. If you teach exoplanets in the classrooms, you should look it up. Teach at the primary school, secondary school, cégep. We have amazing resources for you, so go check it out. And we have these posters that we have made. And what it says at the bottom, it's written in French, so I should really not tell, but it's written rogue planet, which you would probably call a brown dwarf. So we have 2 of these, and we also have the another controversial item. I mean, we we received it today, the brand new mug of IREX, because as you know, we have a new logo, and we had these make, and everyone at IREX wants them, but we did not make enough. So one of you will get one, and all of the astronomers in the room will be very jealous. And the very last prize, I will send it to you. It's a great book. It's called Cosmos. You may know the TV series, but there's a very great book by Andrea, who was Carl Sagan's wife. That's one of my favorite astronomy books, so I always want to raffle it. So, okay, I'll put that aside. Let's just say that the first person gets to choose. Okay. Merci, Erika. 3332. I suppose everyone has that. 646. Oh, you got it. Okay, nice. If you want the book, you can just stay there and I'll come and you'll have the book. Okay, great. Yeah, great choice. I sold it right. And all the others are controversial. So. Okay, 3332 584. 584. Okay, come. Okay. Second to last. 3332 582. Oh my God, what are the chances? It's like maybe in the same group. Oh, it's you. Great. Come. You should have the mug because I wanted to give you one anyways. Yeah. Do you want the poster? Thank you very much. Okay. And the very last. Oh, 3332 589. Yay! Okay. Congrats. Thank you again. If you want to spend some time talking with astrophysicists in the room, don't be shy. They love to talk about their science. And we hope to see you in our other activities and next year for the Grande conférence. Bye-bye. J'ai un élastique.